Good morning everyone. My name is Shiva Krishna. I am from Institute of Aeronautical Engineering from Department of Aeronautical Engineering background. So here we are going to discuss about the subject of aerospace structural dynamics, which is under the topic of undamped free vibrations. So which is under lesson 4. Actually we have been completed the previous lectures. So if you are missed that, please go and read it once again. Okay, here we have been seen about the previous topics, that is advantages and disadvantages and how the terminology, basic concepts, time period and stiffness, what is mass, damping and elements of this particular vibration systems we have been seen. And now we are going to discuss about detailedly what is meant by dampers and how it will be going to be see about these particular topics. So here there is a damper which is we can able to say that there is an absorption of energy. The absorption of energy means if there is an excessive amount of shock or else vibration is created, then it will be going to absorb the all energy and it will try to reduce the particular vibration into the particular time. So here there are dampers in series, there are dampers in parallel. As we seen that previously there is a spring forces in series as well as parallel. So there is a dampers are also in the series and parallel will be there. Spring forces there will be same as this dampers, like there is a excessive shock will be going to be observed. So here it is a damper also will be going to see there is a, like a bushes and springs, rivets, not rivets, there is a sponge like absorbing areas will be going to take it as a dampers, right? So here there is a damper which is under this like a fluid section. Okay, the fluid section which is like a container and the piston. So here there is a masses has been suspended from this series, actual series system and equivalent system. We can able to see there is a C1 and C2 has been merged into this equivalent CE. So if there is a damper in series case, then we can able to write this 1 by CE. 1 by CE is nothing but equivalent damping system. Will be going to be write it in terms of 1 by CE, C1 plus 1 by C2. So which is C1 is nothing but damper 1 and C2 is nothing but damper 2. So which is under CE, we can able to write it as in terms of series, which is C1 plus 1 by C1 plus 1 by C2. So same as it is, if there is a damper which is connected on this parallelly. So if there is a shock which will be distributed equally to these two dampers at a time. So we can able to write this as a, you can see this the diagram. So mass 1 is connected to this damper 1 and damper 2. Yes, damper 1 and damper 2 has been connected. So we can able to write it in terms of mass has been connected to this CE. So CE is nothing but one damper example we have been seen, one damper diagram only seen, which is given as CE. So in these results, CE is nothing but equivalent damper equals to C1 plus C2, C1 damping system, C2 damping system, okay, which will be going to be complete as in terms of series and parallel. Previously as we seen in the springs also, right? So same thing will be going to be taken in terms of series and parallel. Not only here, there is in electrical systems also, you can check it. It will be same as it is in series and parallel. If there is a series, we can able to write it in terms of 1 by, and if there is in parallel, we can able to write it adding of these both. In series only, we will be writing in terms of 1 by summation of 1 by equivalent, 1 by equivalent, right? So introducing this modeling. So there is a physical model we need to convert it, right? There is a physical model we need to be converted into this geometric model as well as mathematical model and combination of geometric and mathematical model. So physical modeling means there is a completely makeover thing will be going to happen like it is in the real world. So which is under the real application, it will be going to be happen into this physical model. And geometric model is nothing but where the geometric absorption is going to be occurred, like where it is in the designing system. If there is a requirement of the damper is there, then we need to be make it as a geometric modeling. And mathematical modeling, if there is a damper, we require to be make it ideal dampers. Ideal dampers we can able to make it is in this mathematical. Combination of geometrical and mathematical modeling means there is a need of this geometrically as well as in the mathematically we can able to say that is a ideal also we can able to write it. So ideally as well as geometric system we can able to write it mostly. And physical modeling which is under this as a physical world we required as a damper. So in the physical practical examples, physical modeling we can able to write it in terms of motorbike. You can check there is a mass of the person. Okay, mass of the person will be written as m, and stiffness of the damper. So stiffness will be going to be check it in terms of legs. Okay, where is the legs will be going to be absorb all the energy and it is try to move to this original position. And damping coefficient CR. Damping coefficient CR will be there is a in pedals or else there will be in shock absorbers. Okay, right? So in this mass of the vehicle body except the wheels, there is a MV. We will be writing as MV. And stiffness of rear suspension, it is rear suspension. You can take it as in this backside tire. There is a rear suspension. We can able to write it as in KS1. KS suffix 1. And damping coefficient of rear suspension 1. Damping coefficient we can able to write it in terms of CS1, suspension 1. Okay, CS1. Here it is a rear suspension and rear suspension, stiffness and damping. And stiffness of front suspension we can able to write it as K2. Front suspension we can able to write it as in terms of KS2. Okay, and same as this damping coefficient we can able to write it in terms of CS2. CS2 for this tire front side. And mass of each wheel we write it as a MW. And stiffness of each tire will be written as in terms of KT. So here this is the physical world. There is a physical methodology that has been converted into this real mathematical model. You can check this. This is a physical and it is in this mathematical. So here it is the MF we have been taken as in terms of complete forces, mass of complete forces we have been taken. And KR is nothing but here it is a KT we have been taken as stiffness of tires, and CR is nothing but here we have been taken as in terms of complete, which is under the complete tire radius, tire dampers. Okay, and MV is mass of the vehicle, and mass of the vehicle has been connected to this rear suspension, front suspension. There is a front and rear suspension has been taken, and weight of the wheels has been connected. And KT is nothing but here is the stiffness of each tire. Stiffness of each tire has been connected here. Okay, and there is a road. It is nothing but mathematical model. So here it is the mass of the full rider and mass of this KT is nothing but stiffness of each tire, and CR is nothing but complete damping system of this particular vehicle. And here it is the motor vehicle mass and suspension 1, suspension 2 of this front and rear wheels, and there is a mass, and KT is nothing but again there is a view of this particular mathematical model. And you can check this simplified mathematical model for this negligible stiffness and damping equations of this rider. So here it is, all MV and MF has been connected here. There is a mathematically it has been given all the stiffnesses from the shoulder mass of the body to this mass of this vehicle. So from head to the rear and front wheels has been connected each, right? It has been converting to this MV and FV. We have been taken in terms of MV plus FV. There is a two masses, right? There is a mass will not be going to be changes if there is a body of this vehicle if we connected, right? Body of the vehicle and body of the person we have been taken in terms of MV plus MF. And rear suspension, front suspension, and mass of wheels and suspension about this front wheel and front wheel tire and as well as rear wheel tire. Okay, KT is nothing but here it is the tire each one. So it has been connected like this, right? So here there is a mathematical model and simplified mathematical model assuming Ks1, Ks2 equals to Ks. Okay, here it is the two tides are there. Okay, two tides are there. You can check this rear suspension, front suspension. Rear suspension, front suspension, there is a both are equally we are taking. S1 and S2. Rear suspension and front suspension is taking as in terms of Ks. There is a complete suspension. So here mass of equivalent, here we have been taken mass of vehicle and mass of person. Okay, equals to we are taking as mass of equivalent. Mass of equivalent we have been taken, and suspension of these both. Suspensions of these both rear wheel and front wheel we have been taken in terms of K equivalent. K equivalent we have been taken. So then it has been simplified mathematical model by assuming Ks1, Ks2 equals to K. Right? So K, it is suspension of K equivalent. Okay, S, here it is the K S dollar symbol. Correct? This is a example from the physical world to this mathematical model. Okay, right? There is an equivalent mathematical model has been given as in this example. So same as it is, which is under this motor bicycle to this motor to this bicycle. So here it is the mass of the rider MR has been taken, which is MR you have taken here, and stiffness of this rider. Stiffness of the rider, you can check this. There is a bending position as well as legs position, which we will be trying to get it as it is in the same position. Where if there is a body is moving, stiffness, sorry, if there is a body is having some stresses, then it is try to move to this virginal shape. It is called as a stiffness of the rider, Kr. Okay, Kr with this damping coefficient of rider equals to Cr we have been taken. Okay, Cr we have been taken, and mass of the bicycle we have been taken as in terms of mv. That is the mass of the full vehicle we have been taken with wheel except the wheels, and mass of the rear suspension, stiffness of the rear suspension and stiffness of front suspension. So stiffness of rear and stiffness of front we have been connected here. Okay, and mass of the each vehicle, each wheel, and here is the mass of each wheel we have been taken as in terms of W. So here it is a CS1, CS2, which is nothing but here it is the damping coefficient of each wheel. Damping coefficient of each wheel. It is to gain its virginal shape. If it is tire is pressing, like in the if there is a ground attachment is happening, so it is try to get all the forces at this particular side. And if you say there is the opposite side, there is a flat. Here you can check this a flat, and there is a some expansion is going to be happen. Right? It is nothing but it is according to the coefficient. It is try to get it is in terms of open shape, right? Damping shape. It is nothing but by the dampers. It is going to get it in this dampers. So there is a two wheels, and there is obviously there is a compulsory there is a damping coefficient of C1 and C2. There is by this CS1 and CS2, which is nothing but tires, front and rear tires dampers, right? And you can check there is a road. Okay, and KT is nothing but we have been taken as in terms of there is a damper of this road and as well as wheels, right? And it has been again given to this simplification. So here MV plus MF has been moved, and suspension of KS plus KS2, which is suspension of these springs, which is complete force. It is try to get it towards the upwards, right? Which is nothing but which is suspension of these wheels. And here it is it has been taken as wheels 1, wheel 2. It has been again taken into this equivalent. Here you can check there is a dampers C1, C2. It is try to get there is a open to this, flat to this open, right? Flat to the open of the tires will be going to be happen. So it has been minimum. So they have been neglected all these things and taken in terms of equivalent of these masses. All these vehicle masses as well as this vehicle of this body, man forces as well, weight as well as in this vehicle parts. So they have been taken in terms of equivalent of these masses, and K equivalent we have been taken in terms of spring system as well as the body stiffness system and dampener system we have been taken, and which is under this equivalent. K equivalent, C equivalent has been taken. Simplified mathematical diagram showing as KS1, KS2 we have been taken as a KS only. There is a spring system. Spring system has been taken in terms of from the wheel 1, wheel 2, which is taken in terms of KS only, and KCS1, which is damping forces of C1 and C2, we have been taken as CS. So same thing we have been taken into this as in the previous as a motor bicycle, and we have been taken as in terms of bicycle also. So here it is a mathematical model has been reduced into this single side. So mass, wheel, one of the mass, one of the spring, one of the dashboard, right? Which is nothing but C. So M, K, C should be there into this particular diagram, which is under the mathematical model as well as in the simplified diagram. Once there is a simplified diagram is there, only 3 elements should be there. So what are the types of vibration is there? According to this actuating vibration, there is a free vibration and forced vibration. According to the extreme resistance, there is a undamped vibration and damped vibrations. So damped vibrations and undamped vibrations we are going to see into this chapter. Okay, in this chapter we are going to see about discuss it detailedly about the undamped and damped system. And according to the motion of the system, there is a longitudinal motion and transverse motion and rotation motion or else translation motion by using of this translation. And according to the behavior of this motion, there is a linear, again like this longitudinal and linear will be going to same, and non-linear it will be like a which is under the upside, downside. There is a motion will be going to be taken into the particular path only. Okay, it is a path motion also we can be able to call. And according to the magnitude of this actual force of this penetration, like in this given time, according to the given time we can able to say that is a deterministic as well as random. According to this, there is a given time. According to the given time t seconds, so there is a random and deterministic models will be going to be presented in these chapters. So first we are going to see about this damped and undamped. Already we have been seen about the free and forced dampings. So here is the examples of this, which is simple harmonic motion pendulum. Simple harmonic motion pendulum, which is free diagram, free vibration. You can check this. There is a spring, ball has been suspended. Once a mass which is having the ball or else which is simple harmonic motion, if it is having suspended, and if you get this, there is a motion if you given, there is a maximum distance it can able to travel and it will come back to its original position. Okay, which is under this string action. There is a simple harmonic motion will be going to happen. So the equation of this point we can able to write it in terms of by this arrow, and you can check this is a longitudinal motion. You can check this the motion of this axis. Only longitudinal y axis will be going to be happens, and transverse motion it can able to move towards the left and right. Towards the left and right it can able to move, like in this A dash, B and C. A, B, C it can able to move towards the 3 position, that is called as a transverse motion. It can able to rotate also. We can talk later that there is a translation motion with a rotation. Okay, and there is a translation motion. It's the only translation motion which is able to rotate like in the fan. Okay, rotate like in the fan. If there is a vibration which is transverse with the translation, like fan is having some motion which is in the under this translation motion, it is very dangerous. You may observe there is a vibration in your rooms. There is a fan if it is turning, so it is like a translation will going to be happen, right? Which is under this small example I am saying. So translation motion you may see in your home, like a fan is rotating, and again if you say there is a fan is having some translation motion also, there is a some physical disadvantage also there. So you can check there is a table fan. You can check there is a table fan which is able to rotate towards the clockwise, anti-clockwise, and it can able to rotate in transverse motion also, but there is no harmful into this because there is a dampers has been attached towards it. So there is a physical world, it can able to attach 2-3 types of motions which can able to make it as an advantage also. You can say there is a ceiling fan, you can check there is a translation motion is only available. Once there is a transverse motion is attached, there is will be going to be dangerous things will be going to be happen. It may be fall, it may be having some troubles over this, right? But if you say it's a table fan, you may see that. Otherwise you can check, there is a diagram will be going to be happens in the Google. You can search it, some any source. So table fan which can able to give the some swing also. Swing will be going to be happen like in the previous olden eras also. You can check there is a swing is going to be happen to circulate the entire circulation of air. It going to be happen to the entire room. Okay, there is a called as a translation with a transverse vibration. And forced vibration, if you say there is a mass has been suspended or force has been suspended, force or mass has been given, then there is a motion is going to be happen. That is called as a free vibration. Like a free vibration, if you say there is a scale, if you have in this hand, if you try to bend it one side, it is going to be give a some certain vibration, right? Or else if you give there is a force into this airplane system, there is a flutter is going to be happen into the larger scale, right? In the smaller scale it may not affect anything, but in the larger scale, like in the flight situation, there is a flutter is going to be happen, then entire body will be going to be collapses sometimes. Then there is a physical models we need to be reduced, like with this in the wings we have been taken as a flexibility. The flexibility we have been taken, it is try to move towards the vibration free, right? Vibration is going to be happen, it is going to be not going to be transferred towards the passenger's cabin. You may see in there is a flutter is going to be happen to this aircraft also, right? There is a flutter is going to be happen to this aircraft, but it's not going to be happen any harm towards the fuselage, because of there is a dampers has been attached towards the edges. Dampers has been attached towards the edges. It will be absorb all the energy and try to reduce the frequencies into this transferring to the fuselage body. And there is a damper free vibrations. We say that there is a damper vibrations. If there is a mass suspended, mass has been given to the spring force and the damping system, there is an example of damping system. And you can check there is a vibration has been continuously reducing from topmost to this within these layers, and because of this damping forces and spring forces, right? There is a mass if there is a given distance or some sudden changes if it is given. U of t means there is a x direction force or u direction force given into this particular time. Okay, particular time if it is given, it is having this larger amplitude vibration to this. It is time. You can check this is the time. It is going to be reduced towards the time. It's not going to be check all the day. Okay, but is the time if it is given 1 second or 2 seconds, it is try to reduce from higher to this lower. That is called as a damped vibrations. Damped free vibration also will go to check it, damped vibration and damped vibrations. So there is a damped vibration. So here it is, once if there is a distance moved or the mass is given with some forces, then it is having some high frequency to reducing frequency. It is going to be lower their frequency by within the time. So here you can check this u of t which is having higher. So in this higher time rate, and here it is a seconds. You can check this is a 0.5 seconds. Within 0.5 seconds, it has been moved towards the higher end to the lower end. As an example, if you say there is a scale in your hand, okay, and if you try to move towards like a one of the side, okay, and if you give the force and give it back, it is having some vibrations in your hand. Okay, you can check there is a physical model, right? So here it is the examples of this. There is a force of this linear vibrations. So linear vibration will be going to give as a peaks, and try to reduce it within a time. And non-linear vibrations, you can check there is a we cannot able to predict which is under this non-linear. It will be going to be happens into this vibrations into this era. Okay, into this non-linear vibrations, it is having some applications into the physical, like in the body massages and everything, because there is a vibration need to be transferred to the nerves within the not linearly. We cannot able to go for these linear vibrations. So we can able to give the massages and by damping system by using of this non-linear systems, non-linear vibrations. Like you may see there is a like in the back pain we can able to reduce by using of vibrations, and fatigue we can able to reduce by using of vibrations. You may check there is a some of applications of in the physical world. So these are by using of these non-linear vibrations only. So in this dramatic vibrations, there is a force we can able to expect. There is a higher and lower will be going to be happens into this time. Okay, deterministic we can able to say there is a deterministic. So it will be going to repeat as the same pattern. It will be going to repeat in same pattern. Random vibration we cannot able to say there is a peak when it is going to be happen, and slant is when it is going to be happen. So this is called as a random vibrations. So in this determinations vibrations we can able to say there is a equilibrium method, energy method, relative method. So in this equilibrium method we already discussed about this D'Alembert principles. Once again we are not going to check it once again. So if you are having any doubt, please go and review these previous videos, and you can check there is the inertial force, spring force and gravitational force, and we can able to write it in terms of which is under the SHM, under the equation of SHM, a square plus omega square x, a square plus omega square x, we can able to write it in terms of a square plus omega square, acceleration plus omega square. So which is under this D'Alembert principle, which is under this all the forces should be equal to 0. All the input plus output will be going to be 0. So input will be going to be k, and mg is nothing but mass and gravitation. Forces should be goes to 0. So comparing this equation to this 2 and 3 will be going to be given as a omega square, which is under k by m. Okay. Omega equals to under root of k by m radians per second. Please remember this as a omega n, omega. Okay. So natural frequency will be given as in these terms. We can able to write it in terms of f equals to omega by 2 pi. Okay, omega by 2 pi we can able to compare with this both. We can able to write it as 1 by 2 pi into k by m. Just replacing this in terms of k by m. Okay, just replacing this omega by equals in terms of under root of k by m. Right, 1 by 2 pi under root of k by m will be going to be hs. So from the equation 1 mg equals to kw, so we can able to write it as 1 by km. K by m we can able to write it in terms of m by g. So from this equation we can able to write it as frequency equals to 1 by 2 pi equals to under root of g by delta also. G by delta also, it is nothing but we can able to write in terms of period, time period, we can able to write in terms of 1 by f. 1 by f is nothing but frequency. Okay, the time period is nothing but 1 by f. If we give, then it is called as a time period in seconds. In seconds, right? So in energy methods there is a total energy. Total energy will be going to be constant. The energy neither created neither destroyed. So it will be converted from one point to another point. It is already said previously, and again it is going to be checking once again. So it is the total energy will be going to be constant. There is a kinetic energy and potential energy going to be constant. So if we are having differentiation also considering the spring mass system into this k in p will be going to be 0. So spring mass system consideration, if there is a spring mass suspended from this at a height h, and we are having this distance x as a force we have been considered, then distance, acceleration and velocity. If you say there is a displacement points in the distance, velocity, acceleration, x dot and x double dot. If you say there is a three forces has been actuated here, kinetic energy will be 1 by m x double dot, m v square, half m v square. Okay, you may check there is a kinetic energy half mv square. There is a movement. The movement, if it is there, then velocity will be going to be happen. So here mx square. Okay, mx dot square. X dot is nothing but velocity. We already said there is a velocity. So here it is a mv square. You can remember, or else you can write it as kinetic energy is nothing but there is a movement is going to be happen. So it will be going to be considered as a half into mv square. Okay, the P is in the form of strain energy and restored into this spring. Stored into the spring the strain energy will be given into this area under the force of deflection versus curve. So you can check there is a spring force. If it is given, strain energy is going to be increases. If there is a spring force, then there is a strain energy is going to be happen. So in this, deflection is going to be set in the upwards. There is a force is going to be taken into this left side. So in this strain energy under this force deflection curve, you can write it as in terms of P equals to half force into x direction, force into this f direction. Okay, there is a force into this x, there is a distance. Okay, we can write it as in terms of P equals to half into x distance and x. So since we know that there is a x in x, here we can able to write it as x square. So here it is a k. So Pe equals to potential energy equals to half into k distance square, k s square. We can able to write it as k s square. S is nothing but square, distances. Okay, k distance square. So we just got this forces. Okay, we just got this kinetic energy means, and here it is the potential energy means. Since we know that the spring force is nothing but kx, we are writing it in terms of kx square, and substituting all this into this previous equation, that is all forces will be going to be 0, right? All the summation of forces will be going to be 0. There is a kinetic energy and potential energy is going to be 0 if there is a summation. So here it is a half into mv square, or else mx square, m dot x square, sorry, mx dot square plus k into x square equals to 0. So here if we differentiated separately, there is a differentiation of both going to be happening like this. Okay, differentiation of both going to be happen like this. So if the square is going to be differentiated, then it will be going to be given as a half, right? If the square is going to be given definition, so differentiation, you may know that there is a, then it will be going to be n in n minus 1, right? Which is under this formula x to the power of n minus 1. So here it is the x to the power of 1, 2 is there. So 2 has been given here. Okay, 2 has been given right here, x to the power of n. If you say there is a, then 1 by n x to the power of n minus 1. So here if we are having like this, 1 by 2 into m, and x into it, x has been presented, and x double dot has been presented over here. Okay, which is nothing but square will be going to be happen, right? Again, there will be complete, we have been taken in terms of x double dot into k by 2 into x will be going to be happens. So once if you are having all these fundamental equation of this SHM, you are writing and comparing this all the equation, omega square equals nothing but same will be going to be happen. There is a k by m. So it is nothing but frequency is nothing but 1 by 2 pi into k by m, which is under this Hs. Okay, which is under this spring forces also, energy methods also. So and Rayleigh-Ridge method, the Rayleigh-Ridge method, it is there is the extension of energy methods which is under displacement of Lord rates. According to this principle of conservation of energy, the total energy is going to be constant. The total energy at the mean position will be going to be total energy at the extreme position. So mean position is nothing but at the middle of this, where we will be, which will be going to be happens into this energy translation. Okay, when there is a translation of motion is going to be happen, there is a translation of energy is going to be happen at the mean position also, it will be going to be extreme position. There is nothing but, if it is in this vibration, okay, the mean position also, at this particular mean position also, it will be going to be high position only. High position will be going to be happen. There is a no energy reducing will be going to be happen. There is a mean position equals to extreme point. Okay, kinetic maximum equals to potential maximum will going to be happen. Then by taking this as an example of mass is moving within SHM, simple harmonic motion, there is a displacement of this body is given by x terms. X is nothing but distance. Distance is taken as in terms of x into sine omega nt. Sine omega nt we have been taken. X is nothing but displacement of the body from this mean position after the t seconds. After the time t seconds, and x is the maximum displacement of the body. You can check there is a small x and here it is a small x. Here it is a small x. Displacement of the body, which is under the t seconds, and x is the maximum displacement of the body after this some mean position. So which will be going to be equal. Okay, there is a distance, displacement, and maximum displacement will be going to be happening at the same time. Okay, when the circular natural energy, okay, circular natural frequency equals nothing but we have been taken as omega n. Omega is nothing but we have been taken in terms of x dot equals to d by dt dx, d by dt of x equals to here omega n x into cos omega nt. So here it is, x has been determined, it have been taken into this outside, and here omega n has been taken in terms of ones. Again it will be considered as one term, sin omega n. So there is a omega n has been considered as one term, and omega n has been taken outside, and sin is going to be negative cos, so cos will be going to happen, and omega n has been written at this time. So at this, which is under the sum of the frequencies. So you may check there is a some partial differential equation has been taken. So again there is a frequency equals to nothing but 1 by 2 pi under root of k by m has been taken into this same way. So in energy methods, where the energy methods are equilibrium method or energy method, when there is a frequency is given, there is nothing but 1 by 2 pi by under root of k by m. Okay, 1 by 2 pi under root of k by m, and frequency is nothing but omega by 2 pi, which is same. Wherever it is, maybe there is the output will be going to be same. Okay, whatever the method you may go, there is a destination will be same. Okay, so in this undamped system, there is a mass has been suspended and has been given a some vibration. There is a distance has been taken by using of these forces. We have been seen already previously. Also, considering the cantilever beam is a negligible carrying mass and concentrated mass at this free end as shown in the figure, and here there is a force has been given and it has been vibrating, started vibrations. So in the free body diagram, we can check there is a inertial force, there is a ma is nothing but mx double dot. So here mx double dot, it is trying to move towards the position, towards the original position, the motion of the body towards the downward position, and there is a three forces you can check. There is a distance, acceleration, and velocity. It is trying towards the moving towards the downwards. Can kx is nothing but it is trying to move towards the x position. That is the same position it is trying to move. Okay, which is nothing but original position. Original position it is trying to move. It is trying to move by using of this k and x movement, k and x positions, right? So by gravitation force is nothing but kg, and it is nothing but equivalent to this distance which is traveling by this x. So we can able to write it in terms of delta also, which is x we have taken in terms of k and delta. Okay, which is inertial force we are having, spring force we are having, and gravitational force we are having, and all these things we are having this equation, which is fundamental equation. It's nothing but acceleration square plus omega square into distance, which is equation equal to 0. Okay, which is going to be 0. Okay, and by using of this comparing of both 1 and 2, we can able to write in terms of omega square equals to k by m radians per second. By natural frequency, which same thing they have been taken in the previous steps. So translation motion also, in this translation motion we need to go for this t, which is nothing but torque, and theta is nothing but angle of rotation. Angle of rotation in terms of theta, which is, it may be from 0 degrees to 360 degrees. It may be 0 degrees to 360 degrees it may go, right? Which is kt is nothing but translation of this spring force, or else there is a, it is try to going for this original position. Okay, there is a force, it is going to be check it by using of this original position, but is a t by theta. T we can able to write it in terms of g by j, g into j. So g into j by l. Okay, this equation you can check this into this equation of translation, equation of torque you can check this t by j equals to g by jg. All these things we can able to check this by using of this equation of translation, equation of torque. Okay, g is nothing but modulus of rigidity, and j is the polar moment of inertia, and L is the length of the shaft, and T is the diameter of the shaft. So polar moment of inertia we can able to write in terms of pi by 32 into d to the power of 4. Okay, which is in the terms of mm to the power of 4. Okay, You can check there is a diagram. And parameters also we have been discussed in previous classes. Once again, you can check this. In undamped system, there is a concentration of disk which is having the mass moment definition, which is under rotation is there. Under rotation is there, which is suspended on a shaft with a negligible mass and shift showing as figure, and angular displacement of the disk is nothing but it has been taken as in terms of theta, which is under the theta has been taken clockwise direction, and torque using of this inertial forces and restoring forces. So inertial force is nothing but I into theta dot IA square. We can able to say there is a simply in terms of linearly, but it is in terms of rotation. It is we can able to say there is a dot of this angular rotation. Okay, and restoring torque we can able to write in terms of T into K of T, K of torque into theta, right? Which is under this torsional rotation. Okay, this is the same thing we can able to say. So into this problem, once again we're going to be check there is a series and parallel connections. So find the W such that the system has a natural frequency of 10 cycles per second. So here we need to be go for this as a 10 cycle per second. If there is a KE, effectively spring mass system of having top of the top spring has been given this series. So here it is a KE is nothing but 10 cycles, right? 10 cycles it need to be distributed per second. K equivalent is nothing but K1, K2, K3. Okay, K1 plus K2 plus K3, which is 3 springs has been connected into this, which you say into this parallelly, right? Not parallelly, it is under series. It is under series, it is there. Okay, and here it is in this parallel is there. Okay, into this parallel and series has been given. So into this we can able to write it in terms of 1 by 10. 1 by 10 we can able to write in terms of 0.0667 kg per centimeter square. And if there is a KE is effectively spring mass system, stiffness has the lowest spring into the parallel, we can able to write in terms of 4 and 5 we can able to write in terms of 1, okay, which is 0.5 we can able to write in terms of 1. KE equal to KE2 equals to we can able to write it in terms of 1 kg per second, okay, 1 kg per centimeter. Now we can know that there is a KE1, KE2, KE1 and KE2. If you say there is a 2 springs are parallelly, and therefore effective force will be 0.0667 plus 0.1, which is going to be 1.67 kg per centimeter square. So natural frequency will be going to be 1 by 2 pi under root of Ke by G by W. Okay, we can able to write in terms of omega in terms of K by W, right? K by W also we can able to write it. So which is under this 10 cycles per second is given. So 10 cycles per second. So we can able to write in terms of, here it is a 111 we have been taken. Also we have been taken this in terms of like this. Okay, 2, 1.5 and 3 has been taken. If we go to this and suspended this 2, 1.5 and 3. You can check this 1.2 plus 1.5 plus 1 by 3. Okay, summation of all these will be going to be given as in this. We can able to write in terms of 0.667. Okay, all these things we have been taken, and here it is a 4 and 5. 4 and 5's values we can able to say there is a from this 4 and 5, 0.5 and 0.5, which is under this K1 have been taken. 1 and 1, 1.5. If we take this, all these things will be going to be happen into this by using of this. So 0.0667 plus 0.1 we have been added together, we have been taken as in this 1.1667, right, kg per centimeter square. And we know that there is a 10 cycles per second has been given. So frequency we know that already. So frequency we have been taken as 10 cycles per second, CPS. Okay, we know that there is a Fn formula, there is a omega by 2 pi. So omega we have been written in terms of Keg by W, Keg by W. Okay, under root we have been taken. Once we have been know that there is a Keg, the G is nothing but 9.80. Okay, 9.81. Okay, 9.81 we have been taken in terms of 980 has been taken. Okay, so 1.667 into 980 divided by 4 pi square. Here it is the root has been taken over there. Okay, root has been overtaken here. So there is a weight we need to be getting, right? Over here we need to be getting. So it has been taken as a multiplication, all these things. So here we have been taken in terms of 4 pi square into 10 to the power of 4, 10 to the power of 2. So we have been taken as a 0.414 kgs, 0.414 kgs. Okay, that has been given into this as an answer. Okay, right? Thank you. All these today have been taken into this as a series and parallel, as well as we have been taken into terms of one of the example also. In next classes, we're going to be discuss about the how the damping forces, how the series forces, and how the translation forces we're going to be calculate into these particular chapters, into these particular problems. Okay, all these problems are going to be given into these practical examples and given with these particular systems. Okay, thank you all.
Like, share and subscribe. Hit the bell icon for more updates.